it can only be canceled with things that aren't under a radical. You can't cancel things that are radical and not radical. Okay with that? Now I'm going to show you one more example. I'm just going to show you what, I'm a little bit behind my early class. I want to make sure we have plenty of time to work with the adding and subtracting. So I'm just going to show this example. Don't worry about writing this down. I'll scan this in. But you're going to see this in homework. That's the main important thing. So I really just am going to show you what I've already written, just so you can think, when you see this in homework, you think, oh, that's what she was talking about. Okay? So this is a more complicated example. It's not something I want you to panic about, but it just gives you some ideas of things you might the things that might happen and you need to be aware of. And the main one is this problem right here. Let me erase the part here that I marked that was not there. Okay. So, given this problem, which has two different radicals, but notice it also has an outside coefficient. Sometimes you have an outside coefficient. Now, the important thing to remember is that coefficient on the top or the bottom? It's on the bottom. This is a fraction. And if something's on the bottom, can you just magically move it to the top? Hopefully the word magically was a clue that the answer is no. No math in that, no magic in math, right? So if that's in the denominator, basically, it must stay in the denominator. Okay? So if you've got a coefficient that's on top, it stays on top. If you've got a coefficient on the bottom, it stays on the bottom. Now there is a coefficient up here. What is it? 1. So you can write it in. And hopefully that will help you see, this is like a coefficient of negative 1/5. It is not a coefficient of negative 5. That would change its value. 5 is different from 1/5. Okay? So placement in a quotient matters. Okay? Now I just pulled it aside, put it out of the way. It's going to be part of our final answer, but there's nothing to do with it right now. I just want to deal with the radicals, and the radical rule only applies to the stuff in the radicals. So that just gets pulled aside. And we deal with the radicals, put them under one house. Okay. This is still dragging this along, flatten this out to be 2. Of course, be mindful of your exponent rules. 2 minus negative 2 was 4, not 0. It's not 2 minus 2, it's 2 minus negative 2, or 2 plus 2. And then, that might look, sometimes the simplest ones confuse the brain enough more too. Because this is, got a leftover bit. This one's perfect square, but that's a leftover bit. So when we broke it up, I'm still dragging along the coefficient of negative 1/5. And 2x to the 4th, I put the perfect square in front and the leftover bit second. I went ahead and also just put this over 1, just to keep everything, because I know I've got this on the outside, it just kind of keeps everything, it reminds me everything's a quotient, and what's on top stays on top, and what's on bottom stays on the bottom. Okay. So of course I could root and release this. Okay. This was square root of x to the 4th, root and release to become x squared. And leftover bits stayed locked up as a radical. Okay. And those were both on top, so they stay on top, but then when I smush this back with it, the whole thing's negative, and this is the 1 is the coefficient on top, so we don't have to write it, and the 5 is the coefficient on the bottom. There's nothing else there, so we have to just put the 5. Okay. So like I said, don't worry about scribbling this down. This is kind of a most complicated example. You'll see something similar in the homework as far as dealing with coefficients outside your quotient rule. And the main thing is, remember, if it's on top, it stays there. If it's on bottom, it stays there. Changing between numerator and denominator is an illegal move.
That's for the homework 11.4 or 11.3?
It's good at the end of 11.3, the end of what you saw last time. Yeah, there may be 1 or 2 that have coefficients. Just remember, where they are is where they stay. 5 is different than 1/5. Okay. So let's move into adding and subtracting now. Okay? So that finishes what the homework has already been posted. That's the end of that homework, working with those quotient rules. So 11.1 and 11.3 was all about multiplying and dividing. Okay? Product and quotient rules of radicals. Now we're going to bring in addition. Okay? And that's where this, just like adding versus multiplying terms makes a difference, that same rule applies to adding and multiplying radicals. Okay? So different rules for addition than there are for multiplication. Okay. So this is an 11.4. And this is the first half of the homework that's been posted for 11.4, and the second half will be multiplication, which I hope to introduce before you leave, but we're going to focus on next more completely next time. So, adding and subtracting radicals. Okay. Now, trust me on this, and this is the same thing I'm going to say when we get to the second half of 11.4, which is multiplying radicals. You already know the rules. They're looking different to your brain because we're dealing with radicals instead of just x's and y's. But the rules have not changed. All the rules for real numbers that we have been doing with regular terms with x's and y's and exponents are going to be the rules that we use for radicals. Okay? And that is that just like with addition of terms, we have to have like terms. Multiplication of terms, we just have to have like bases. It's the same idea with radicals. Okay? So for adding and subtracting radicals, you must have, just like adding and subtracting terms, you must have like terms. For adding and subtracting radicals, you must have what's called like radicals. And like radicals, just like terms are same base, same exponent, like radicals have two things. They have to have the same index. They must both be squares, both be square roots, both be cube roots, whatever root they are. It must be the same index. And they must have the same radicand. Right? Whatever's under the radical sign must be the same. So, for example, some examples of like radicals would be, say, square root of 3 and 2 square root of 3. Same index. What's the index of these? 2. Yeah, square roots. And what's the radicand? 3. What's under the radical sign is the radicand. Okay. Now, they have different coefficients. What's the coefficient of this first one?
1.
Yeah, and this one is 2. Okay. So these are like radicals just like these are like terms. X and 2x. Okay. These are like terms. Okay. Well, in the same way, these are like radicals. You can pretend your radical is an x. And this is 1x, and this is 2x. 1x and 2x. Okay. So your basic kind of combination then requires like radicals just like you're required to have like terms. Let's say you have x plus 2x. What does that equal? Yeah, 3x. Yeah. You've got a 1 there. Huh? You don't have to write it, but you have to know it's there, so you can write it in, so you do the math with it. If your variables are the same, like terms, same base, same exponent, then you just combine with addition or subtraction your coefficient. But the x stays the same. 1 apple and 2 apples is still 3 apples. Okay. So if you have square root of 3 plus 2 times the square root of 3, what do you have?
2 squared.
Okay. So do we have like radicals? Okay. So just like when we have like terms, we combine the coefficients. What's the coefficient here? Okay. We have same index, same radicand. These are like radicals, and so this becomes?
3 squared root.
Right. 1 plus 2 is a new coefficient of 3, square root of 3. Now, can we do anything to put these together? I mean, they're both 3's, right? Are these both 3's?
No.
Ah, no, they're not. Why aren't they?
That one's square root of 3.
3 has one value, but square root of 3 is not actually 3. Square root of 3 is 1.73, and then it goes on forever. It's an irrational number. Okay. So you cannot mix. This means 3 times square root of 3, but if one thing's a radical and one thing's not, just like you can't smush them together, you can't cancel things out. You know, that's an illegal move. Radicals and non-radicals do not have the same value. Okay? You can't mix them. Okay? So that's the basic idea. Your brain already knows how to add like terms. Okay? We are following the same rules. We just have to understand what a like radical is. It follows the same rules. Okay? So some examples of unlike radicals. Just like unlike terms might have an x and a y, or an x cubed and an x to the fourth, okay, either different letters or different exponents, or unlike terms, unlike radicals either have the different indices or different radicands, or both. Okay. So unlike radicals, for example, might be 3 square root of 7 and 4 cube root of 7. Why aren't these like radicals? Yeah, this one's a square root and this one is cube root. Different indices. If you put square root of 7 in the calculator and then you put cube root of 7 in the calculator, you've got two different numbers. Two different irrational numbers, but different. Okay, so unlike indices, unlike radicals. If you were asked to add or subtract these, you couldn't do it. You'd walk away.
Just leave it at that.
Yeah, if you were asked to put 3 radical 7 plus 4 cube root of 7, then you would not add 3 plus 4 to make 7. Because this would be like 3x. This would be like 3x squared plus 4x cubed. Unlike terms. That would be like saying, yeah, 3x squared plus 4x cubed. Yeah, same base, 7, but different exponent, different indices. And you'd walk away. You're done. Okay. So these would be done. Both of these. Okay. Another example of unlike radicals would be, say, negative square root of 5, which of course has an, what is the coefficient here? Negative 1, right? You have to do the math with it. But the radical itself is square root of 5, and then we've got 9 square root of 3. These are both square roots. They have the same index, but they have different radicands. What the coefficients are is meaningless. Okay? If you have this like radical, you just combine the coefficients, whatever they are. They don't have to match, but the radicals do. Okay with that? Okay. All right. So, a couple of sort of basic things to look at. I'm going to give also more of sort of this mixed list next time because you're going to have to really understand when you're confronted with these problems. First thing your brain says is it plus or is it multiplication? Okay? And that changes everything. So, what is square root of 5 plus square root of 5? And what is square root of 5 times square root of 5? 2. Here? 2. Square root of 5. Right. This is like 1x plus 1x. This comes back to x plus x. If our terms are the same, we just add the coefficients. And if our coefficients are 1, it's still 1 plus 1. So this becomes 2 square root of 5. This is square root of 5 doubled. You add something to itself, and it becomes doubled.
Would that just that one, the next one?
Mm-hmm.
The next one would just be 5, wouldn't it?
Right, exactly. When you I hinted at this last time, and this is going to become much more important moving forward, is that by the product rule, these have the same indices, right? Excuse me. So by the product rule, we can multiply them under one house because they have the same index. Well, that just means we got twin factors, and a twin is the root. Okay? Or, to take the product rule further, that's square root of 25, and square root of 25 is 5.
Or wouldn't it just be like square root of 5 squared and then squared and
That's another way to look at it, exactly. This is the same thing as square root of 5 squared. And that index of 2, we've been working with exponents on the inside that cancel out the index. But an exponent on the outside also cancels out the index. Either way, you're left with 5. Yeah. The index of 2 and the exponent of 2, whether it's on the inside or the outside, obliterate each other, and it releases, it blows up the radical, and it leaves the radicand. Okay. So when you're multiplying a radical times itself, the answer is the radicand. Okay. A radical times itself obliterates the radical. It just cancels it out, and your answer is that radicand. Now, by the product rule, just to be clear, you don't have to have like radicals to use the product rule. The only way you can add radicals is if you have like radicals. Okay? Just like for adding, you have more rules for adding. You have to have like terms, which is same base, same exponent. To add radicals, you have to have the same radicand and the same index, like radicals. But for multiplication, all you have to do is have like bases. With radicals, all you have to do is have like indices. Okay? So just because those radicands match, well, it gives us the special rule of it killing the radical sign and the answer is the radical, but that doesn't mean you have to have like radicands to multiply. You just have to have the same index. Okay? See, there's 2 rules for addition. There's 1 rule for multiplication. Okay? It's a little simpler. So, if you've got, say, square root of 3 times square root of 7, can we do that? Okay. Let's compare it. Square root of 3 plus square root of 7. Can we add those? Same index, but different radicands. These are not like radicals, right? Okay. So, you're done. But can you multiply them?
Yeah.
By the product rule, you can. They have the same as long as they have the same index. Then this means 3 times 7, or 21. Okay. Just like terms, x plus y, you're done. Okay. But if you've got, as long as you have the same index, they can go under, the product rule says you're fine. Now, if you've got, let's say, coefficients too, let's say 2 times the square root of 3 times 4 times the square root of 5. Okay. Well, just like when you have coefficients, when you multiply, you're just multiplying numbers. That doesn't change. 3 times 4 is 12. 2 times 5 is 10. That doesn't change. Okay? But then with the variables, you add the exponents. Here, you just multiply your coefficients, but then you deal with your product rule for radicals. Okay? So, what's our new coefficient? 8. This is multiplication, right? And then our new radical is 15. Yeah, we just multiply them under 1 radical sign. Now, could we add 2 radical 3 plus 4 radical 5? No. We would not do 6. 2 plus 4, we can't do that because these are unlike radicals. Again, this one's done. Unlike radicals. But we can multiply them. The radicands don't have to match to multiply them. If the radicands do match, then you got this special rule where you kill a radical and your answer is the radicand. When you square a radical, it just kills the radical sign.
So, same for like test purposes, like on the exam, we get one of these questions, and we just go ahead and just write 5 instead of like the whole set.
Like this one here?
Yeah.
Exactly. I want you to see that cancels it out. Yeah. Anything, a radical times itself, which means a radical squared, obliterates the radical, and your answer is just the radicand. And yes, you don't want to have to write all this out, because when we use this property to start multiplying at the end of this chapter, and yet next time, you don't want to slow yourself down by writing all of that. Yeah, put it in your notes, understand why it's true, but you want to get automatically, a radical times itself, the whole point of that is to obliterate the radical. Okay? A radical squared is just the radicand. Okay? But if they don't match radicands, that's fine. The product rule still combines them under 1 radical sign. Okay? And the coefficients in this case are multiplied, whereas here the coefficients would be added if you have like radicals, which in this case you don't. In this case you do. Okay. So let's put that together in some bigger problems. So if you've got 5 square root of 3 minus square root of 3 plus 8 square root of 2. You've got 3 terms there. You've just got to decide if any of those terms can be combined into a single term. Well, as long as you have like radicals, you can combine. Out of those 3 terms, do any have like radicals? The first 2, right. These are all square roots, so that's not a problem. No, indices are all the same. But these also have the like radicands, so they can be combined. And so what's our new coefficient?
4.
4, because there is a 1 here. 5 minus 1 is 4. And what's my radical? Yeah, that didn't change. This is like 5x minus 1x. 5x minus x, 4x. Yeah, and that's as simple as that one gets, because that one is not a like radical. And so you don't make this 12 something. This is not 12 square root of 6. This would be 32 square root of 6 if that were a times. But it's not. So you're done. Negative 3 square root 200 minus 5 square root of 8 plus 9 square root of 98. It looks like it at first because those are unlike radicals. They're all squares, square roots, but yeah, they're different radicands. But you can't actually answer the question of whether you have like radicals until all the radicals are totally simplified. And so with 3's and 2's, yeah, 5, 7's, any prime number radical, those are already simplified. Even some non-primes are still simplified. You can't, you take them, the square root of 10, for example, is not prime, but you can't simplify it any further because it doesn't have any square root factors. But remember, this is not a perfect square. If it's a perfect square, then take care of that. If it's not a perfect square, maybe you can at least partially simplify it. So you don't know that you can't combine these until all of them are in simplest terms. Okay? So here's where you got to stay organized. You've got a coefficient on the outside, but I also have a non-perfect square here, and I want to know if I can break it down into, at least partially simplify it. Okay? So I might be able to root and release part of it, which I would then multiply times the negative 3, and I'd still have a leftover bit. And once I do that to all 3, I'd look at the leftover bits and see if any of them are like radicals. Okay? So you got to be organized. You got to deal with 3 terms here. Now, when I say be organized, I've still got a negative 3 on the outside here. Okay? Now, I've got square root of 200. I'm going to break that up into 2 houses. Because 200 is not a perfect square. But I'm going to go off to the side and make a list of the factors of 200, or I'll do it on my calculator. Okay? And when you do, and I'll do this one on the calculator, if you do y equals then 200 divided by x. Okay? And then second table, let's start at 0. If you go down the right there, you immediately hit a perfect square. I just want to caution you because if you keep going down, there's another perfect square. And by the time you turn things around, you're going to end up finding like another one, at least 4. Okay, so there's more than one perfect square. So be very careful when you're doing your list, whether you do a manual list in writing off to the side or whether you do it on the calculator, you make sure you're looking for the biggest possible perfect square. Okay? You're going to make things really messy if you choose one that's too small, because then you have to do another step to finish it. Okay? So, since this is 100 times 2, then I'll write the 100 and 2. And by the product rule, I can put it under 2 houses. Okay? So I just rewrite square root of 200 as square root of 100 times square root of 2. But I also have the negative 3 in front. See where I'm going with this? Perfect square is on the left, so I'm going to be able to root and release that, but that stays locked up. Okay? So let's break the rest of these up too. 5, and now 8. Perfect square? Maybe it's a perfect cube. Is it a perfect square? No. Does that have any perfect square factors? Yeah. Hopefully you can do this one mentally because there's not a lot of factor pairs of 8. 1 times 8 and 2 times 4. What works? 4. So put the 4 first. Okay. So I didn't change the value of anything. Just by the product rule, square root of 8 is the same thing as square root of 4 times square root of 2. Making sense? Okay. Plus, the 9 is the coefficient. 98, not a perfect square, with a manual list on your calculator. You make a manual list, just remember, always go in order, just like the calculator would. Start with 1 times itself. Hey, then you go in order. 2, well, it's even. You got to think kind of your divisibility rules. If it's even, 2 is a factor. And then 2 goes in, 49. And there's more factor pairs, but can I stop there? Yeah, because as soon as I'm going down this right-hand side, as soon as I hit a perfect square, I know that's the biggest one. Okay? And you'll say the same thing on your calculator list. So I'll write that as 49 first times 2. Oh, look at my leftover bits. Yeah, those will be like radicals once I root and release the part that I could. Now, this is negative 3 times, what's square root of 100? Yes, it's not the square root of 10. Remember, you're not only rooting, you're releasing. Root and release. As soon as you root it, it is released. And then leftover bit doesn't get released. Minus 5 times the square root of 4 times the square root of 2. Plus 9 times 7 times the square root of 2. Once you root it and released, then you can make your coefficient nice and neat. Got negative 30, 10, 63. I've got 3 terms here. Are any of them like radical terms? All of them. So you're going to be able to turn 3 terms into 1. You just have to combine your coefficients. Negative 30 minus 10 plus 63. Yeah. Negative 40 plus 63. Square root 2. All right, you do this one. Leave that up there. So you do 6 square root of 75 minus 4 square root of 50 plus square root of 12. If you like radicals to add or subtract, you don't have that now, but don't walk away until you make sure everything is in simplest form. Because you don't know if you have like radicals until everything is totally simplified. None of those were perfect squares. If they were, I just go ahead and root and release them. They weren't. But they all did include perfect square factors. So by the product rule, I broke each radicand up into 2 houses. Will I be able to simplify this down to 1 term like I did the first example? No. I'll only combine the like radicals, which are those 2. This does not become 12 radical 6 or whatever. Unlike